Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We're continuing our study of Chapter 4 on entropy, and in this lesson we're going to look at how we can use those fundamental relations to calculate entropy change for solids and liquids. We're going to begin by looking at the fundamental relations for ds equals whatever. And we can use either of the two forms, but the one that's going to make a little clearer definition, I suppose, is to work with the ds is equal to d over t plus p over t dv. The reason this one is nice is that we know that for both solids and liquids, no matter how much additional pressure you apply, the volume change is going to be very small. So comparatively, this term will be essentially zero compared to du over t. Now, the other thing that I know for liquids and for solids is that both du and dh are very close to being equal to each other for solids and liquids, and we can define it to be c sub p dt. That means that, and this is the specific value, ds is c sub p dt over t. Now, a couple of different special cases. For cases where c sub p is a function of t, then I would say that delta s is equal to the integral from t1 to t2 of c sub p over t integrated with respect to t. But there are some cases where c sub p is not really much of a function of temperature at all. This is the case with solids almost always, and for liquids with small temperature changes. In those cases, delta S is very close to being equal to C sub P, the natural log of T2 over T1. C sub P is a constant, dt over T gives us the natural log of T. So this is going to be exact, but this is a good approximation for solids in all cases, or for liquids where the temperature change is not that large. Let's use this to work an example problem. In this case, we want to calculate the change in internal energy and the change in entropy for liquid water that's being heated from 20 degrees to 50 degrees C. In this case, the delta T is not particularly large, and so we can use constant C sub P. If we look that up, C sub P for liquid water is about 4.184 kilojoules per kilogram Kelvin. If I calculate delta U or delta H, this is going to be C sub P times delta T, or 4.184 times 50 minus 20. 4.184 is kilojoules per kilogram Kelvin. 50 and 20 are in degrees C, but remember delta T in degrees C is the same as delta T in Kelvin, so therefore this will be in units of kilojoules per kilogram, and we get 125.5 kilojoules per kilogram. If I calculate delta S using C sub P natural log of T2 over T1, C sub P is that 4.184 kilojoules per kilogram Kelvin, and then the natural log of the ratio of the temperatures. Remember that I must change to kelvins. These have to be absolute. So 273 plus 50 over 273 plus 20. And this answer is 0.408 kilojoules per kilogram Kelvin. Now what happens if we were to use the data tables? So using the data tables, I'm going to just simply look up saturated liquid in these. So delta U is 209.5 minus 83.4, which is 125.4 kilojoules per kilogram. We only vary in the 4th decimal place. It's less than a 0.1% error. Delta S is going to be 0.7038 minus 0.2965 equals 0.4073 kilojoules per kilogram. In this case, we vary in the 3rd decimal place. It's a 0.2% error. In both cases, this is well within plus or minus 1%. So for most calculations, this would be very adequate. But what about if we have a gas? For that, we need to move to the next video lesson. Thank you very much for your time.